Hi, in this video I'm going to do part one of lecture one, which is measuring matter. So this is going to be a brief overview of how to use units, conversions, scientific notation, anything else that we might cover in physics. So this is more or less a review for most of you, I hope. And if not, this is a really good refresher. So this is part one. So what I want to cover in this lecture is to talk a little bit about models, scientific notation, SI units, metric prefixes, and eventually, probably in part two, I'll cover the conversions, how to make conversions, because it's very important to convert the simple notation from meters to centimeters, etc., like that. Okay, in this first section, I'm going to talk a little bit about modeling. So as we know in real life, modeling is, well, as we know, real life is pretty complex. So what we're going to do to kind of eliminate some of the complexities of real life is do this thing called modeling. And what we do in modeling is we basically take those complex systems, I'm just going to move this down, there we go, and just make them a little more simple. For example, an object in free fall. So generally when we look at objects in free fall, when you take an object and just drop it, it's under the influence of gravity, but it's also under the influence of air resistance. And to make things simple, we usually take out air resistance. So that's an example of models. So even though there's real things happening in our real environment, we take them out to make them a little more easy. So another thing that models do is help us provide a law or some sort of way to analyze the system. So, for example, as I used before, objects under free fall experience the same acceleration if we take out air resistance. So if we take out air resistance, our model becomes much more simple. So although this right now probably looks like hieroglyphics to you, this is way easier to analyze than using air resistance, because at that point you have to use these things called differential equations and it gets kind of complex. So we can model laws with both explanations and, of course, mathematics. The point of doing that is being able to make predictions. For example, if I know exactly how long the object has been falling for, I can actually get a pretty accurate depiction of the distance, assuming that air resistance is not a huge factor. Another word that's used in physics besides model is called system. What a system does, again, it simplifies your model. So, for example, when we're talking about collisions and conservation of momentum, you'll notice that the word is the system. So even though in real life there's the road, there's air resistance, there's more mass in the front of the car than the back of the car, there's a lot of things that contribute to this system, but we usually just ignore most of it and just talk about and assume that the mass is the same throughout the car, that there's no friction involved. So when we say our system, it all usually involves more than one object, so you can see there's two here, and we basically once again simplify the situation. So in all cases, when you start off with a problem, always oversimplify them before you make them more complex. It's a really good tactic to tackling those harder problems. So once we got our systems and models together, now we're going to take some measurements. So when it comes to taking measurements, we like to just take some, well, not necessarily shortcuts, but some manageable ways to, to deal with these large and small numbers. So that's where scientific notation comes in. And then we can also use metric prefixes to kind of help with that as well. So we don't have lots of numbers trailing after things. And then part two of this, like I said, I'll talk about converting from different scales and using different calculations, etc. Um, like I said in class, we will not use significant figures as it's not super important in physics. Well, I mean, it's important for research, but when it comes to our values right now, we're not going to worry about it. But your homework will ask for significant figures, so it's not a bad idea to use this website right here where it goes over the basics of significant figures. So, for example, if it says to the two significant figures, generally it wants, a number with two numbers and the rest of them are zeros, kind of idea. I know that wasn't a great example, but the best thing is just to review on your own. Some of you might have experience, some may not. I'll let you kind of tackle that on your own through your own experience. So scientific notation, it's basically removing the excess zeros, whether it's to the right or left, so big and small numbers. So as a quick example, in physics generally, if you get a number like this in your calculator, it's much more easier to display it like this because you get an order of magnitude of how big that number is. And generally that's what we want to look at. Yes, we're ignoring the preciseness of the measurement, but in essence, we just want to get an estimate of the value for the most part. And then vice versa with the small number. Notice that this is a lot of zeros. It's easier just to put it to the eighth like that. I'm sorry, to the negative eighth. So just as a reminder, to do scientific notation, you find your decimal place first and decide, where that is. So here it is right here. And if we move to the left, like this example, this is going to be a positive number. So why don't we do that? So if we count together, 1, 2, 3, 4, 5, what we do is we move the decimal place to this location right here, like that, just like we have here. And the amount we counted goes up here in the exponent. So notice I counted to 5. I'm just going to demonstrate one more time. So 1, 2, 3, 4, 5. Decimal place goes in between the 5 and 6, and we say times 10 to the 5th. So that represents this number in scientific notation. Now when we go to the right, a negative sign pops out. That's because we're going smaller, where this one was going bigger. So we will go the same idea in terms of how we figure out the scientific notation. So I put the decimal place here, and then I count the zeros. 1, 2, 3, 4, 5, 6, 7, and I keep going until I get to the end, so 8 right here. So I'm not going to stop right here. I want to go so that there always is one decimal place between the numbers. So I got to put it right here because otherwise I still have a 0. So I'm going to put it here. And when I do, that's where the 8 comes from. And since I moved to the right, that's a negative sign like that. And same thing, notice that I stopped when I put the decimal place between two numbers like this. And it had to be non-zero numbers. So notice that I had to actually move it here so that it wasn't in between another 0. Now, yes, a 0 will come out of here. That's okay. Or you can ignore it if you notice I did here. But this first number has to be a non-zero. So notice that this is non-zero, and this 5 was a non-zero number. So that's how far you move the decimal place. And again, I'm assuming this is pretty much review. There you go. Here's another visual of what I just did if you want to kind of follow along here. So I'll skip this for you to take a look at. So an important thing in physics or any sort of measurement is the understanding the unit of that. It's how much of the object you've measured, and it's extremely important. $5 is different than 5 cents. And if you notice, it's the same number but different units. I mean, $500 is different. If someone owed you $5 versus $500, that unit piece really matters. I mean, it also matters very much so when it comes to measurements. Because 5 meters versus 5 miles, well, those are two different measurements. So as quick examples you can see here, so 5 meters represents a length, meters per second, the unit is a speed. And for our physics class, we're going to deal with a Newton, which is a unit for force. So the units are the letters that are attached to the numbers. They tell us what the quantity is measuring. So yes, it's very important to the point where in any test or quiz, if you don't put the units down, I do penalize you. And it's not because I'm trying to be mean, it's because they absolutely matter. I can't read your mind, so I don't know if you represented 5 meters or 5 centimeters or 5 inches. So once again, it's very important that you put these values in there. So the basic units in physics that we're going to focus on are called the SI units, which stand for Standard International. As you might imagine, all science wants to be consistent in the same type of measurement you make so that you can make comparisons. So for example, if I wanted to measure mass in the United States, I'm going to use kilograms. And if I were in Australia, I would also want to use kilograms. So if I did one experiment in the United States and one experiment in Australia, we have something we can compare by. Now, of course, there's different reasons for different units, etc. Yes, there can be differences. I mean, even our gas is measured in different units. In America, we measure it in gallons, and in Europe, we measure it in liters. So yes, this is not always true. But for our purposes, we're going to try to keep things as consistent as possible. So that's why it's SI units. So a quick, just examination of what we have here. So the unit of mass is a kilogram. So it's not how much something weighs, it's how much stuff it has. So that's mass. Length is a measurement of some sort of distance. So when we do that, it's going to be the meter. So it's about 3 feet. So that's how we make most of our measurements. Volume is going to be the liter, which should actually be a capital L, so I apologize for that. That should be capital L, but more or less a liter. We won't use this unless we do any sort of gas properties. Force, the unit is in Newton as a capital N. Temperature can vary. Sometimes you'll see it in Celsius or Kelvin. Either way, these are our temperature. And once again, we won't really use temperature in this course. And time is generally in the seconds. It's very common to use seconds. So if you're in hours or years or days, whatever the unit you want to convert back to seconds. So just some information of where these numbers come from. They come from these standards, if you will. So a meter comes from the definition of how far light travels in this amount of time. So it's a very specific amount of time that light travels. That's what a meter is defined as. A kilogram is based off of mass just sitting around somewhere in Europe. That's where we define a mass. And the second comes from an oscillation period of a cesium atom. So the last thing I want to talk about is the difference between base and derived units. The main thing about base and derived units is that derived units is a combination of the base units. So the base units are the dimensions that we mentioned earlier, which is dimensions of mass, length, time. You can have Celsius for temperature. But a derived unit is basically the two base units. So a unit that you might be familiar with is density, which is mass divided by volume. And when you do that, you can see that density is in fact kilograms over meters cubed. So even though it's a volume, we're still using the base units and we're raising it to the third power like this. So if you know your base units, you can derive most of your derived units. So units such as energy or density or force can all come from and be derived from the base unit. Metric prefixes. So once again, I'm assuming these are some familiar measurements that you've done before, but metric prefixes basically take the basic measurements and make them bigger or smaller by adding a prefix in front of it, hence the word metric prefix. So for example, the meter is our base unit, but if I put the word kilo in front of it, I've now made it a larger measurement. The kilometer or kilometer is 1,000 meters. So as you can see with this scale right here, it's a pretty big measurement. We can go the opposite way as well and measure something small like the centimeter. So adding centi means 100, so there's 100 centimeters in 1 meter. That's where it comes from. But as you can see, the prefix is centi, which represents a smaller measurement. And we can continue forward and do the smaller and smaller with the milli and the micro and the nano, etc. So here are the metric prefixes. So there's some interesting ones which we'll probably never use, like the decameter or the hecto. But things I'd like to just highlight here is the pico and the nano. We'll use that in electronics. The micro is pretty common in charges. The milli, you'll see that for small measurements in the centi. The kilo is 1,000. Mega is 10 to the 6. So you can see all the powers of 10. So you can see how small. And a really nice way to memorize these is, if you notice, they mostly go by threes. We usually skip the twos, but 1, 3, 6, 9, 12, 1, 3, 6, 9, 12, as you can see here. So using metric prefixes, we can get an order of magnitude of how big that measurement is. And this is the metric ladder. Some of you might be familiar with this. So when you go to the left and to the right with the decimal place, it changes the value like that. So I'll save this for part 2, where I'll show you how you can convert from the different metric prefixes.